So hi, yeah, welcome everybody. Today, hopefully you're aware, but we're going to be looking at electrification of heat, particularly in and around multi-effect evaporators and similar sort of process technology and unit operations. These units sort of particularly relevant in the food industry, but also in other sort of associated industrial sectors as well. And ourselves at Cool Planet, we've been looking at a range of sort of exciting heat pump and tertiary unit options that can really help to recycle the energy available in these kinds of processes and move you from sort of thermal fossil fuel based emissions, scope one emissions, towards scope two emissions, which if you are buying renewable energy or getting those certificates to certify your electricity is carbon free in essence, then that can do significant impacts on those scope one emissions profiles and those scope one emissions reportings. Because that's one of the main drawbacks of the multi-effect evaporators. They're really, really cool, but they do use, they are energy intensive. And as we've been looking at these sort of studies for various clients in various sectors, there's some interesting real nuggets come up as well in other areas about potential sort of niche applications involving things like combined heat and power recip engines, providing the electricity in certain profiles can work as well. And other interesting areas of sustainability around water savings, eliminating seasonal variations in vacuum by eliminating the requirement to have vacuum, and so on and so forth. So hopefully Charles is ready to share his wisdom with us all. But like one of my first experiences with evaporators, I worked in the distilling industry, and it was a key part of the industry was co-products. You generated a lot of co-products. Some may call them waste streams, but were in an agricultural process. They were co-products and they could be reused, sold on into the animal feeds market and so on. Typically in malt distilling, you had sort of pot ale and draff, a liquid stream that had some good suspended solids in it, and a heavily solid stream with some moisture in it as well. Now, in theory, that draff could go straight back out to sold to cows and sheep and so on. The pot ale, which was a liquid, say that generally had to be treated, and the application of choice was in essence tended to be sort of twin effect falling film evaporators driven under vacuum with MVRs, and they were really smart. They're really big. They concentrated that product and allowed you basically to eliminate a vast amount of its bulk, the water, in essence, and you could get that off into the food chain as well. Other sites, because you're small distilleries, you might actually sort of send it to one central location, a distiller's dark grains plant, where they actually take the draft as well and combine that all up, use some drying technology as well as evaporators to produce that distiller's dark grains. But one of the things I always remember is as the climate change levy came in the UK and in Scotland in particular, if you had an evaporator on site to treat your pot ale, you got a different level of allowance, if you will, almost on energy. If you were just a straight distillery, small distillery, you might have to do X kilowatt hours per litre of alcohol produced. If you had an evaporator, you were allowed, X plus Y kilowatt hours of electricity or thermal energy per litre of absolute alcohol produced because you were, treating your co-products. And obviously the dark grains plants, if they were just standalone, in essence, effluent processors, they had their own metrics. So it was recognized as within the industry as it's quite an energy consumer, a significant energy consumer, but it was serving that purpose, which was to produce a better product, a higher value product to go out into the market. But the technology lends itself really to, looking at it these days with a potential view from electrification. And in other industries, which Charles, I'm sure, can come on to there, is where you've got multiple effects, 3+ effects up to 8 or even beyond. There's great potential there for reusing the steam, but instead of doing it from a thermal point of view, if you switch that to electrification, take that waste heat as a prime, you can really have some startling gains in terms of scope one emissions reductions. Would that be fair to say that, Charles? I'm not overselling it, am I?
No, I think you've done a great job summarizing a lot of hopefully what we're going to talk through today. But yeah, so a bit of my background. I've been playing around in evaporation space for most of my career. I've it's widely applied, so you see it very commonly in sugar processing, both from corn beet and cane. You see it very often in salt in a lot of the biotech industry, where you're taking a fermentation product and upgrading it. To your point, Colin, yeah, it's common in ethanol to take that residual syrup and reconcentrate that up to get rid of the water after you've recovered the ethanol. I think what's really interesting is historically mechanical recompression evaporation has been around. It's typically only been used in the really big plants, because traditionally electricity has been expensive and fuel has been relatively cheap. And I really think today that traditional way of operating has changed a lot. I mean, the price of fuel has gone up substantially. Carbon is increasingly an issue, and so that ability to switch and electrify is really interesting. The historical challenge with mechanical recompression is typically that it's a single effect evaporator. And so if you try and do all of your work in that single effect, you start getting the boiling point elevation that raises that boiling temperature higher and higher. And if you have a thermally sensitive product like a sugar or often a protein, you don't want to get it too hot, because you start worrying about, breaking it down, coloring of sugars, denaturing of proteins, that sort of thing. And if you're in the milk industry, where they also do quite a lot of evaporation, obviously those hot surfaces are a great place for the solids to concentrate. And if it gets too hot, you end up fouling up your heat surfaces more quickly. So multi-effect evaporation definitely has its place. The drawback the advantage of multi-effect evaporation is you're dropping the pressure in each of those effects so that you can reuse the steam. So in each of the effects, the boiling fluid is getting cooler and cooler as you go to lower and lower pressures. That's great from a process perspective, but it means that the vapors coming off of that last effect are fairly low pressure and fairly cool, which makes it difficult to reuse that heat in a traditional system. I think the furthest I've seen it go is in some of the sugar plants, where you have 7 or 8 effects and then maybe a crystallizer at the end. But what you can do is you can grab that heat through a heat pump now, raise the quality of that heat, and then bring it all the way back to either all the way back to the front end of the evaporation train, or if you don't want to spend the capital to go to that high of a pressure, partway through the evaporation train. And really what that buys you, I think, is the ability to reuse existing equipment. But it also moves you from the fuel to an electricity basis. And so as Colin said at the beginning, you're eliminating scope 1 and possibly picking up scope 2 carbon emissions. But if you are smart about the electricity that you're using, those scope 2 emissions can be smaller and or eliminated through the use of green electricity, which is increasingly becoming available today. So it's a really interesting shift in the marketplace, where fuel is getting more expensive and there's a carbon tax. Electricity is getting slightly cheaper, but avoids that carbon loading. And so the optimal place to run your plant today is maybe shifting pretty substantially.
Yeah, I mean, we've been installing heat pump solutions as part of Cool Planet for over 12 years, and those initial applications was all on economics. Decarbonization was not really as fashionable back then it was now, and these places where they worked on an economics basis was generally typically off the natural gas grid. If they may be using LFO or other oils for their thermal supply, so inherently more expensive fuel. Electricity was just typical grid electricity, but they're off that natural gas grid. So typically these were, meat installations, and they're very low margin commodity type markets, operations and so on. So, any way they could improve P&L, they would be very open to it. And the quicker the payback, obviously the better. And that's still a given now as well. So they were really looking at, and in these meat industries as well, it should be worth saying, is their temperature profiles, which is important on the heat pump solution, is they use a lot of water at 45 degrees and at 60, 65 degrees, 40, 45 for hand washing, so on, and 60, 65 for CIPs, hygiene, wash down, so on and so forth. So an inherent in a meat process as well as a lot of heating up of the product and a lot of cooling down as well, because what do you need to really drive a heat pump solution, as we're touching on, is that sort of industrial waste heat source. It's the exit from a 7th or 8th stage on an evaporator, or it's the total heat being rejected from a refrigeration plant, for example, typically may have ammonia as a refrigerant or some other kind of refrigerant or F-gas in there that goes to maybe an evaporative condenser or a cooling tower. So instead of just rejecting that heat to atmosphere, that's your actual heat source prime for the heat pump. Grab that, bring it in, and they say on standard ones, first stages, and we'll come on, Charles will come on to a little bit more about what we're doing about first stage, second stage, and tertiary, is typically those heat pumps can take that heat rejected from, say, a refrigeration plant and easy, comfortably give you 60, 65 degrees Celsius water. The COP, coefficient of performance, which is in essence the efficiency of operation of the heat pump. You could get COPs above 4, 5, 6. What that means, for every unit of electricity you have to put in and drive that, it would give you 4, 5, 6 units of thermal energy out. And typically electricity broadly 3 times as expensive as thermal energy. So if your COP was above 3, you would get an OPEX benefit, an OPEX saving. So if you quickly think in your head, LFO is actually versus electricity, that ratio is maybe 2 to 1. Therefore, a COP 4, 5, 6 is giving you big OPEX savings. And that's how we installed heat pumps way before decarbonisation was fashionable or even a thing. The weird thing coming out of the pandemic, and COP26 was at the tail end of 21, coming out of that. Charles, you'll testify to this. We have been non-stop almost on doing advanced heat pump studies, electrification options. There seems to be a bit more emphasis and priority placed on this. Paybacks, which may have previously been, we need sub 2-year simple payback. A lot of industries now accepting maybe 5, 6, 7. Others, typically the farmers who are taking the longer term view, they're happy to take even longer if they're getting step changes in their emissions reductions. Not tinkering, but going for it. Yeah.
I think the key thing to say there, Colin, is a lot of these projects pay for themselves really attractively. In the last few years, the price of fuel has skyrocketed. In Europe, certainly the price of carbon has gone up a long way. So a lot of projects that were 7 or 8 year paybacks are now increasingly 1-2 year paybacks on that basis. The other thing is electricity is increasingly decoupling itself from the price of fuel. And so that traditional spark gap of electricity is 3 times the cost of fuel on a kilowatt per kilowatt basis is less true in more and more markets these days.
Yeah, for sure. Just the other week there, the carbon was above €100 a ton for the first time, I think ever, almost. It spiked really close at previously. And if you look at the range of forecasters now, obviously, if I could forecast price of carbon, price of fuels and so on, I don't think I'd be doing this webinar. But broadly, what the market's saying, there's maybe 5% of the guys who look at that saying, oh yeah, it's going to come down. But 20%, 25% are all, it's 100 with little bits of increases. Most of them saying, no, it's going to go up year on year. And the range is staggering. Some are at 175 in a few years' time, and others are above €300 a ton of carbon. Now, that's only in sort of bigger-ish emitters at the moment, but the one thing we know in Europe, once they start, it starts coming down to the smallers. And if you're fortunate to escape it from a direct emissions point of view, you're going to be seeing it on the bills soon enough as well.
I think the other thing to say, though, is it's not necessarily just the government action and the markets that are going to drive this stuff. A lot of consumers are really driving these days towards green credentials are increasingly important. A lot of companies are making those scientifically backed claims in terms of carbon reduction. I think whether or not the market forces it directly through pricing, the consumer and advocacy groups may well have a significant say for a lot of products as well. And the food space is often heavily brand based, and so being able to claim those green credentials certainly doesn't hurt.
I'm getting my 10-year-old sort of chipping me for why I've not gone to an electric car yet. So it's certainly in the Zeitgeist of the younger ones for sure. So is it maybe worse, Charles? We talked there about first stage and second stage and tertiaries and so on. A lot of food producers and a lot of fixed installations manufacturers, outside the food sector, they'll use steam, right? Because steam, as we mentioned, historically feels relatively cheap. Steam's a great medium to transfer heat around, transport it, send it to a user, so on. You generally will generate that, this is really broad, but 10 bar, because you save on capex, pipework size, so on. You take it along. A lot of users, not most, I'll say a lot of users, 1, 2, 3 bar gauge is fine to use it. So you step it down at point of use into a bigger pipe, blah, blah, the user uses it, etc. What I think a lot of people might say, oh yeah, but I need steam. A heat pump won't give me steam, which on a first stage is technically correct. It's absolutely correct. It won't. However, you can get to steam through being clever and smart on it. And secondly, you don't have to replace all that infrastructure because you can get the steam. And therefore, this is actually simply generate it from thermal, switch it to generate it from electricity, is in essence the principle we're sort of looking at.
Yeah, no, that's a great point, Colin. I mean, I think what you end up seeing is yeah, historically heat pumps have grown out of the refrigeration industry, and so they've used traditional refrigerants like ammonia or the R gases, and so they're really good at collecting heat, all the way down to -40, -60 if you're in a blast freezer. But I mean, the sort of heat pump applications you typically see are collecting heat at 10 to 30 centigrade and warming it up to sort of 60 to maybe these days as high as 90 centigrade. That's a real sweet spot for those traditional refrigerants, ammonia, for example. And that's really good if what you've got is heat that would otherwise go to a cooling tower, and you want to make heat to do CIP or hand washing or those sort of wash down processes, sort of sanitary water at 60 to 90 centigrade is a real sweet spot for traditional heat pumps, and that works really well. The beautiful thing about doing that is usually you would otherwise dump the heat to a cooling tower. A cooling tower essentially is just a really great big water evaporator. So if you're able to use a heat pump to capture that heat, you then don't need to send it to the cooling tower. And if you don't send it to the cooling tower, you don't have the water bill and the water treatment associated with running all that water through your cooling tower and evaporating it. That's great in places where you've got a bunch of water stress or where you're increasingly being forced to, reduce that water level. And if you don't have a cooling tower, but you're sending the water to a river or taking it from the sea, that is again, you're usually limited on the volume and the return temperature. And so this is a great way to stretch out that resource further. The nice thing about a heat pump is, as Colin's alluded to, you're not throwing the heat away. You're upgrading it and keeping it inside of your process. So you're saving on the water. You're spending a bit of electricity to get there, but you're then reusing all that energy internal to your system. Okay, so that's your traditional, so what we tend to call stage 1 heat pumps, and those are good up to, as I say, around 60, 70 centigrade. What we've been seeing recently is that there's some really interesting developments using alternative refrigerants. There's some complicated R gases, but even traditional stuff that we would think of as liquid petroleum gas, so propane, butane, those sort of gases. Turns out there's really nice technology that exists in the oil and gas industry for compressing those gases. Those compressors, while large, can be redeployed into a lot of the food industry and related industries that we've seen. And those are really good at picking up heat at the sort of 50, 60 range and upgrading them to 120, 130, maybe a little bit higher. What's nice about that is then you've got a bridge that can get you from hot water that you would maybe get off of the final stage of an evaporator train, or in other scenarios, the hot vapors leaving a dryer, or the top of a distillation column in a ethanol plant, or those sort of applications. Grab that heat at sort of 60 to 90, upgrade it into steam, and now you can either directly use that steam locally. To Colin's point, historically, it's easy to, like with an electricity generation grid, right? You have a giant generator and then high pressure steam through a lot of pipes over your whole plant. You don't have to think about it. You just tap into it where you need it. That's great if fuel is cheap and steam is going to be ubiquitous. But what we're increasingly seeing is there are applications where you sort of localize that capability, like putting a solar panel on your house and charging your own electric car and running your oven with it. You can do the same thing if you put the heat pump in locally next to the dryer. or next to the evaporator train, you can then upgrade the heat back to the front end of that evaporator train and maybe never go into the 10 bar steam network, just stay at 2 bar, 3 bar, and save yourself a bunch of pain that way. The final thing I'd say is the sort of the third stage that we've been looking at is there's a lot of existing steam compressors. So the world of mechanical recompression has been around forever, and it has been a really solid market for particularly in the sugar industry to upgrade the heat off of a single stage evaporator. Turns out those guys have been doing a lot of work as well, and those steam compressors are increasingly able to work in the vacuum range, so they can pick up heat at as low as 60, 70 centigrade, but they can compress it all the way up to 10, 20 bar steam if you really want to. It's a question of how much energy and how much money you want to spend on it. The key point, though, is that those steam compressors are super efficient, and so you can drop those in and get your heat from atmospheric kind of levels up to 3, 4 bar to the front end of an evaporation train, and do that really cost effectively from a capital perspective and really efficiently from an operating cost perspective as well. So there's some really interesting new developments and capabilities that are opening up that are really changing the game in terms of what's capable. And Colin, I'm sure you can talk to one or two of the applications we've been.
Yeah, I mean, one of the studies we've done for a client in the associate a sector associated with food and beverage, the potential there was, if they did the full scheme, which was a first stage, a second stage, and an MVR technology in there, they could get 99% plus of their scope 1 reduced. We also gave them a sort of smaller scale one as well, that would get sort of 40% scope 1 reduction. We've done actually in the process of implementing a stage 1 heat pump solution for Irish producer Bulmers. That's going to get a minimum of 42% of their scope 1 reduction, and then that in essence allows them, if they wish, to go further into the second stage and maybe the tertiary as needed, but they won't need as big a units at that point as well, because we've mapped their profiles. We understand where they're using the heat source available there, as well as this will be a nice sort of closed loop almost, and it gets rid of that one specific user. You said, we're not going to tie into a big distribution network. If they're going to be used on 5 or 6 users elsewhere, we sort of tie it in that little closed loop there. And they've also got the fallback, excuse me, that they've still got a full steam capability as well. So from a reliability point of view, there's N+1 redundancy there as well. If there's an issue with the grid or the pump is out for maintenance or whatever, they've got steam, they're not going to impact production and so on. And I suppose that comes back to one of our raison d'etres for being is, whilst these solutions are absolutely fantastic and we know that they can deliver because they've been used in oil and gas for years and years and years, you don't necessarily think of butane and propane as refrigerants. I instantly think of that as campus stoves and camping. You've got a butane bottle. Everyone knows butane bottle, but it's not. It's actually a refrigerant as well, weirdly. So getting your head around that is always fun, I find. But actually, in a lot of industries, we come across a good example is a food processor. They had evaporators and dryers. They ran 4 lines, multiple lines, sorry, and in a batch process. But they were, simple things when we come in and model these plants, which everything starts with a model to understand how the evaporators are working and so on. But here in some of these examples that I'm sort of citing, is they have the ability to actually do some sequence changes, do some process heat recovery and integrations. They've got multiple stages. They're not actually being smart and sophisticated enough on the existing heat reject, bring that back in and close all their existing loops. And some of them can get staggering performance improvements, step changes, those 40, 50, 60% figures from actually integrating and intensifying the existing process before then having to consider what may be an exotic step of moving to a different kind of generation technology. It's not that exotic, but if you're starting at a low base, there's potentially great mileage in just evaluating yourself from a modeling perspective, particularly for evaporators and multi-unit operations like those, because if they're not spot on, if you're not recovering all the heat, if your pressures are off and so on, you can be operating them very suboptimally, which is a lot of wasted energy that can be recovered just from being sensible and smart, which I think, Charlie, that's one of our main starting points, particularly for some of these sugar industry studies we've been doing, is looking at exactly their existing process and saying, well, actually, you could hone in here on these steps A, B, and C, and even other processes before then the heat pump would come in. So you optimize the consumption first and foremost, and this is very relevant for refrigeration sources as well. Optimize that total heat rejection first, making sure you're operating in an optimal fashion, so you get almost a free set of savings, and then go for, yeah, let's go spend some money and do it big style.
Yeah, no, I wholeheartedly agree that that is a key piece. I think it's always great to find the magic bullet, the single silver thing that'll save everything. I would hate for anyone to walk away from this thinking that heat pumps are just a magic bullet that's going to save everything. They're not. They're a tool in the arsenal. They're a really powerful way of reusing heat. But absolutely, to Colin's point, what you want to do is look at your whole integrated process, see how things are interacting and working, and apply the right technology solutions to that integrated system. The fun thing is that the right solution really does depend a lot on your local conditions and your local markets and the existing capital that you have in the ground. So sometimes it makes sense to go with a butane heat pump. I should say, everyone always worries with butane or propane, it's an explosive gas. Oh my goodness, what's going to happen if I put that in my plant? Do I have to be safety rated? There absolutely are safety concerns. You have to consider those. But it's a refrigeration loop. It's a closed loop system. So the intent is the gas never leaves that closed loop. It stays inside. So in the same way that today a lot of food plants have ammonia used in their refrigeration plants, ammonia is toxic and explosive as well. But it's not a huge issue because if it's well managed, you keep the ammonia encapsulated inside of the system and it just goes round and round without ever touching the process or ever leaving. Taking a step back, though, if you look at that big integrated system, what you're trying to do is understand what capital do I have on the ground already? What solutions can I have to tweak that capital to reduce the overall energy use before I apply a heat pump? And then, if it makes sense, put in something like a heat pump. To Colin's earlier point, what's really fun in our job is that we get to go to places where we see all sorts of varieties in terms of the relative cost of fuel and electricity. As Colin's alluded to, sometimes you go to a site where they have a grid connection for electricity, but they're piping in light fuel oil. That's often a great location for us to try and look for a heat pump because that spark gap, that the cost of fuel versus the cost of electricity is enormous. Other places, they're paying a lot for electricity, but they're sitting on an oil field or a gas field, and they get the fuel for peanuts. In those scenarios, what's kind of exciting is you can try and integrate heat pumps with something like a combined heat power process where you take that locally available cheap fuel, and it could be anaerobic digester gas off of your own site, for example. Take that cheap fuel, upgrade it into a mixture of heat and electricity, use some of the heat in your process where you need that higher temperature, higher quality heat, but then use the power either to just run your plant or to upgrade some of the waste heat with the heat pump so that you really start getting an interesting integrated solution where those different pieces play to each other. But it's a very localized picture and a very sort of custom view of what you're doing. And then the last piece, and Colin can talk to this far better than me, that's really interesting is a lot of these solutions. It's great to have the consultant come in and drop in a solution and thank you very much, we're out of here. What's critically important is to make sure that the value that you've created through doing that is maintained and continues to pay back 6 months, 2 years, 5 years down the track. And so really sort of tying it all together with a good data management and a good performance management system is a key piece that you want to keep an eye out for.
Yeah, definitely. I mean, that's again one of the core elements of our offering. When we work with industry, is it's very much data and monitoring and management coupled with services and in IP and these kinds of solution development. So we're not a typical consultant. Here's a report, go and knock yourselves out. It's here's a study, and we can help you implement it. all the way through, and we can also monitor, track, and what you were touching on there, the flexibility of assets. Now, if you have a CHP already, the heat pump can come in and complement that, and you can actually then start to look at a lot of clients we have now have PPAs as well with renewable generators, as you can then playing the markets is maybe a strong word, but you can have a flexible approach to how you manage and operate your assets. So again, you have that N+1 redundancy in certain areas. You can switch a CHP off or turn it on, or switch the heat pump off, and vice versa. So understanding process and understanding, you can't just turn certain processes off to reduce demand, whether that's power or thermal. And similarly, just turning it on, these things take time to ramp up. So we understand that, but is where our software, Cool Planet operating system, Cool Planet OS, can come in. That what we can now start to do is advise maybe a day in advance. For example, wind is going to be really strong tomorrow. You have a wind PPA, you're going to have copious amounts of cheap power available. Therefore, turn the CHP off to make savings there and use your heat pump to drive as much of your thermal consumption and demand as possible. Similarly, and that might be for a few days, day ahead's quite good on wind, because weather forecasts are broadly, believe it or not, broadly accurate within the 24-hour period. We wouldn't be saying in 10 days' time, turn it off, because things can change. But that flexibility of approach, particularly when you've got island markets, Ireland, GB, other jurisdictions are sort of leading the way, because as they try to get more renewables on the grid, they need more flexibility of demand, whether that's consuming when the wind is blowing, in essence, or when the wind dies, turning off, dampening down demand as well. In mainland Europe, because there's more interconnections available, that market's not developing, but it is going to come. One of the big trends as well is moving transport to electric. We're going to go from ICE engines across to electric, and on that basis, you've basically got a mobile battery that can be charging or can discharge on demand, in essence. And that's where that's moving, as Charles touched on earlier, the decoupling of electricity price from, in essence, the natural gas price is going to have to happen just to continue to get more renewables on and provide that flexibility. So there's no way in 10 years' time that grid electricity can still be directly, closely coupled to gas price. You may start to see your electricity bills parsed out, renewable price, the fossil, based on the amount of generation in a period or something like that. Could be one way that starts to happen. So positioning yourself with a view to that, I think would make sense. I think as well as we touched on, these solutions can sort of seamlessly integrate within steam infrastructure or site infrastructure, so on. And I think we touched on, was maybe worth going back as well, just mentioning around, it's not just evaporators. We're focusing on evaporators today because we've come across quite a few in the last sort of 12 months. But, the spray dryers, other aspects, distillation columns are suitable as well. Basically, what we're saying is any sort of process industries, for want of a better description, where you've got big chunky assets on continuous or near 24/5 operations, pretty much would be open to being reviewed. And these applications are potentially suitable. Obviously, an optimization, looking at all your set points, modeling and optimizing your existing assets, that works for practically anyone. But what we're saying is actually quite a broad number of units or applications or processes can benefit from the sort of heat pump plus tertiary unit potential solutions as well.
Yeah, excuse me, absolutely. I mean, sounds a bit weird, but I increasingly get excited when I see hot, wet gas. I mean, there's a lot of dryers. There's a lot of places where there's a lot of water leaving with the process. Historically, some of the most efficient boilers that you see have been putting have been putting condensing economizers on the discharge stacks, because the fumes leaving the top of the boiler or the furnace often have a fairly high moisture content. They're 10-20% moisture. If you cool that down to 50 C or so, a lot of that water condenses out, and that water is essentially steam and it's giving up a lot of heat. The same is true, though, if you've got dryer exhaust or warm gases leaving a distillation column. So those applications, I think, are really interesting places to scavenge for waste heat. I mean, Traditionally, that big plume that you see leaving is a lot of energy leaving the plant that we could otherwise capture. The other area that I think is really powerful, and Colin alluded to earlier, is if you already have existing cooling assets, refrigeration systems, or chillers, that is actually giving you relatively low grade heat. It's 25, 30 centigrade typically that you can be discharging that at. But that's heat that you potentially can pick up and use as well. So depending on the application that you're looking for, there's some really good places, and the nice thing about that is it's energy that's being thrown away otherwise. So it's going into water evaporation or into the sea. Colin?
Yeah, no, I mean, I think touching on there as well, if you're having to use cooling tower water to drive a vacuum, uh,
Yeah.
a fringe benefit, which potentially is much more than just being a fringe benefit, is if you put a heat pump solution in, you actually could take away the seasonal variation of your vacuum. You could be getting a consistent, potentially deeper vacuum year round, independent of wet bulb temperature and how hot it is, which as you move to the sort of lower latitudes or higher latitudes, if you're in the southern hemisphere, towards the equator, in essence, it does get difficult in the summer. We have some processing clients based down in Turkey, Greece, Israel. That's a challenge in the summer for sure.
Well, as someone living in the States, there's even at northern latitudes in the middle of the continent, there's some pretty substantial summer to winter swings.
Yeah, for sure.
But yeah, that decoupling of your process from the ambient temperature, getting away from the dependence on the wet bulb for your overall process systems, can really be a big piece. The one thing that we touched on, but I just want to make sure that we emphasize is just that general greening of the grid. Colin was talking about some of the challenges of renewable power entering the grid, in that it's much more variable in terms of the supply and demand. So the wind doesn't always blow when you want it to, and the sun irritatingly sets every day. So solar has limitations as well. What's interesting, though, is pretty much everywhere around the world that those applications are really taking off. Solar, wind are becoming cheaper. They're becoming a bigger and bigger fraction of the overall market. So where historically electricity has been viewed as a potentially fairly dirty Scope 2 carbon heavy component of the fuel or of your carbon footprint, increasingly and pretty much everywhere in the world, that carbon content of electricity is dropping. There's places, obviously Scandinavia and so on, where there's a lot of hydro, France where there's a lot of nuclear, where those numbers have always been relatively low in terms of the carbon content of the electricity. You go to places like the UK, they've been putting a lot of money and time into wind and related things, and you can really see that carbon content of the electricity dropping. So while it's always worth considering those PPAs and greening your Scope 2, it's going to happen eventually and gradually, no matter where you are in the world. So picking up electricity, the grids are all going to go greener as time goes on, I think. So
yeah, that's a definite macro trend, Charles. I mean, even in China, they're coming down from 700 grams per kilowatt hour, and it's more down sub 600. Now, it doesn't sound much, but it's actually 15% reduction, considering they've got so much coal inherent in country, if you will. And similarly, Poland is similar as well, which is a lot of coal, cheap, readily available, a big industry as well. But that too is coming down. So yeah, that macro trend of greening of grids is happening. So yeah, you can piggyback on, if you're not already on a renewable situation in terms of your power and Scope 2, you can certainly piggyback on the greening of the grids. And it's another argument as well on electric cars, which is, if you're just coal powered, electricity is equally as dirty, if not dirtier, than petrol, which is technically true, but that's not the case in most jurisdictions. Is the grids are going to green, and can't really see that reversing, to be honest.
Yep. No, I agree.
Cool. Well, I think Charles is looking at the time there, and we don't want to keep everyone too long. I think if we were to sort of summarize my main takeaways there, there's probably great opportunities to do that fully retrofitting of existing process unit operations and so on. But everything would come from doing an initial model, evaluating the assets and seeing what could be optimized initially in your existing assets and portfolio before then looking at the multi-stage heat pump solutions, which includes those tertiary units if needed, and how they could largely integrate fairly seamlessly, whether that's tying into networks, tying directly into users, or both, which could happen as well. We think, macroeconomics, I think everything that's happened in the world in the last 12 months, certainly the pressure seems slightly off on electricity and natural gas prices just now, but that carbon price trajectory is going upwards. If we were betting men, I think we're saying in a decade's time, electricity should be decoupling from fossil fuels, maybe not decoupled, but decoupling. And pretty much any major continuous process, not even necessarily continuous batch works as well, but basically heavy duty dryers, distillation columns, potential application there, but it all requires study and looking at. And the final one, is CHPs, taking away your vacuum seasonality, and other sort of condensing economizers could come in as well. There's other sort of niche applications that, it's not a one size fits all, go and do this. You should always look at your current conditions, where you are in the world, your geography, what your supply's like for thermal and power, and there'll be something pretty cool that can fit in there. Really, it's only very
Yeah,
occasionally we get stumped.
I think you're absolutely right. I think that's a great summary. I think the one thing I'd throw in as an adder is, change is a constant, and so the right solution right now isn't necessarily the right one for 2 years down the track. So keeping track of how your system is performing and really understanding what it's doing is a key component to making sure that you derive the full value out of your system.
Yeah, brilliant.
But,
Well, cool. So thanks for your time,
yeah.
Charles. Thanks for everyone who's joined us today for their time. If there's any questions, queries, comments, feel free to reach out and get in touch. Email's always good. Phone numbers kicking about as well somewhere, no doubt. But yeah, thanks everybody for your time. Hope it was of value, and
Fax or send a pigeon even.
we'll maybe see you again on something similar in the future.
Thank you very much for your time. Great to talk to everyone. Thanks, Colin.
Thanks, everyone. Bye bye.
Goodbye now.